Thanks, Rory, for your kind introduction. Slightly daunted by this occasion, and I chose this title, Promises and Pitfalls. I hope it'll be more promises and less pitfalls. The title is on biomarkers in cardiovascular disease because that's probably what I've spent those almost over 2 decades studying. And when I started, I suppose I had done my doctorate in Dublin, MD degree for National University of Ireland on the homocysteine story, and we believed probably about half of cardiovascular disease was explained by the big risk factors, the smoking, cholesterol and blood pressure. So there's a great search for these other factors, these elusive factors that might explain the remainder. So much of what I'm going to talk today will be perhaps an extension of that debate. What I'm going to say very much represents teamwork, because I see epidemiology as teams, and I think Richard Dahl acknowledged this, that it's very hard for an individual to make a substantial contribution nowadays with the way epidemiology has gone. But if you can work together as a team and work, and CTSU and DPH afforded both the collections, as well as the people to work with, statisticians, bioinformaticians, laboratory scientists, and it was this synergy of the collections and the people has made those 2 decades very fruitful. So in my reflections back, hopefully I'll give you a taste of that, but I want to look mainly on the future, on the promise of what's to happen. This is me lecturing in the MSc. You can see varying degrees of engagement of the students. I'm looking at social media and scanning their devices to see when this guy stop whittering away. But the truth is, epidemiology is a multidisciplinary science. So it does require that knowledge of biology, as Rory alluded to, as well as the epidemiology. The molecular biology, the nutritional epidemiology, our discipline has greatly expanded, and it's not possible for one individual often to encompass all of that, but in fact by working with the people and selecting out of those, you can engage to help answer some of these questions. It's worthwhile pointing out some of the limitations of the disciplines that we have. This audience knows this, but you'd be surprised how many eminent epidemiologists ignore the importance of confounding and interpreting associations. You only have to read the Daily Mail, open that to look at lack of association of saturated fat with coronary artery disease. Have we got it wrong? And the whole monographs on this topic where people are looking at observational data, relating associations or lack of associations of saturated fat with coronary disease, and a failure to appreciate the validity, the reliability of those associations, and then try to advocate changes based on half-baked hypotheses. Randomized trials, yes, randomized trials are the paradigm. They're at the top of the pyramid, and the meta-analysis of the randomized trials on the top of the pyramid of evidence of study designs. That's what we teach our students. Small trials and subgroup analysis within trials are highly susceptible to the effects of chance. Bias in the recording of outcomes, that can seriously distort results. So in CTSU and most of our work, we've tried to focus on trying to get together these meta-analyses of the randomized evidence where possible. So in my work, I very much saw the epidemiology as trying to get the science behind the trials, or trying to find those the questions that we could then test. And in some instances they've worked. Some instances we're still struggling to make them work. This slide is familiar to all of you. Here we have on the left deaths from vascular disease in middle age in the UK, men, age 35 to 69, and on the right over 70 to 79. And we're familiar with this curve, that's the all cardiovascular disease, and underneath that are the components of that, the ischemic heart disease, stroke, and other cerebrovascular disease. So you can see it peaked here in males in 1970s, declined by about 2/3. So the Whitehall study that I started off work on was set up in 1970 at the peak of the epidemic. And that study gave us an opportunity then to look and monitor then the effects of risk factors and changes in these risk factors over what was happening with cardiovascular disease in the United Kingdom. We're particularly interested in this changes in middle age. And here's the study. And I got introduced to epidemiology. My boss sent me to Cuba, and we had a 10-day seminar of epidemiology. A 10-day seminar was 2 working weeks, and I was attached to Geoffrey Rose for 1 week. And Geoffrey had set up the Whitehall study. And really listening to him and those questions that he posed at that time, it reflected for me how to ask the right question in epidemiology. That was important. And the question was about, does lowering moderately elevated blood pressure prevent risk of cardiovascular disease? How do you design a study to answer that question? Geoffrey had done the MRC trial. They were planning the MRC elderly trial. This was the era before Rory and Stephen did the meta-analysis of these trials. But there were serious questions. And the other week was with Jerry Stamler, and was on how do you design the optimum diet for the American population to prevent cardiovascular disease? And curiously, those 2 questions have remained with me, and they became the topic for my MSc when I did the meta-analysis of metabolic ward studies with Richard and Rory after my year at London School of Hygiene. And then the blood pressure trials, I've worked with the group in the HIVET trial, Roadmap trial, and Jan Stassen in Belgium. But here, back to cardiovascular disease. Half of the survivors had died. So I wanted to do look at this for my master's thesis, and Richard looked at the data and said, oh no, you can't possibly do a master's thesis on this. The exposures are 40% of smokers. You've got unreliable data. You have to do a resurvey of these. So that was the start to the story, and we did a pilot study in 1995 and then resurveyed the remaining survivors in 1997. So it's a relatively modest cohort. About 15,000 of the 19,000 have died. You see that pattern, about half of the deaths from vascular disease, and of those with vascular disease, about 2/3 of those were from coronary disease. I want to contrast that then with the China Kadoorie Biobank study. So for the last 5 years, I spent most of my time working on this. So it's 30 times larger. It's 500,000 people. These were a survey of 10 regions in China between 2004 2008. They've had 2 resurveys then of 25,000 each in 2011 and 2013, and now about 10 years of follow-up. And in these, there's about 25,000 deaths, and about 38% of the deaths were from vascular causes, and on this occasion, about 2/3 of those vascular deaths are from stroke, in contrast with Whitehall. So I want to look at the contrast between these 2 studies. One gives prolonged exposure data, and the other one gives far larger data, and both are set up around the peak of the epidemic in their populations. So one of the lessons from the Whitehall resurvey then, well, there were 2 real lessons. One was the magnitude of the changes then in the cardiovascular risk factors. So it's set up in 1970, so the Royal College of Physicians report, the original 20-year follow-up of the British doctors was published, and at that time, shortly afterwards, smoking cessation in male civil servants working in Whitehall, and they stopped smoking rapidly after joining the study. Here's the subset of survivors. So there's the same individuals who were alive in 1997 compared with 1970, and you see an absolute difference then in the prevalence of smoking of 20% reduction, slight increase in risk of diabetes, blood pressure increased by about 16 millimeters of mercury, and mean total cholesterol increased by about 0.5 millimole. Now if you look at China Kadoorie Biobank, we see similar mean systolic blood pressure, this sort of prevalence, about 5% diabetes. If you look overall, much higher prevalence in male smokers, but prevalence not dissimilar, and a total cholesterol of about 4.5. the big lesson initially from the pilot study, and then it was confirmed when we did the whole survey, was this within-person variability over time. So when you stratified the population into fifths, with the lowest fifth here in the top line, and the top fifth in the bottom line, there was a 52 millimeters of mercury difference in the range, and that's what we typically plot on the x-axis when we're plotting blood pressure with risk of disease. Keep that ranking in those individuals in 1970 and look at the mean values in 1997, and that difference in range of systolic blood pressure is down to 17. So these individuals, they all went up, as we said, the mean went up, but there's a shrinkage in the range. And that pattern was also seen for total cholesterol. The difference between 3.5 in the lowest group, 6.9 in the top group, a range of 3.4, and that had truncated to 1. So Richard was very fascinated by these data, and these about the magnitude, because we didn't have data sets that had this degree, this extent of follow-up. We often do studies where we design studies in middle age and then follow them up over time and make conclusions about differences between middle and old age. And in this era, there was a big debate in the UK that cholesterol wasn't predictive for mortality in old age, and blood pressure had lost its predictive value, and hence the design of the HIVET trial. So it was the interpretation of this epidemiology, and we went to the Framingham study. I'm sorry this doesn't project that well. The Framingham data so it's the same phenomenon, the same period of time, 26-year interval between the baseline values. So individuals at baseline were ranked into fifths, and then every 2 years in Framingham, where they had resurveys, that phenomenon, they were plotting here their mean systolic blood pressure, and similarly their mean diastolic blood pressure. So the range here is dropping down from 57 down to 15, or in diastolic blood pressure from 32 down to 9. So you can see that truncation, that shrinkage, and you can plot that shrinkage either as a correlation or as this ratio of the ranges. And that phenomenon is actually very widespread in epidemiology, and we hadn't appreciated that, and that relates to many different exposures. Say for height and for BMI, maybe that don't vary that much, it's not true, it's not the case, or for factors that are largely genetically mediated like Lp(a), but for many of the other variables. If you looked at, for example, electrolytes, which we did, sodium and potassium in the UK PDS, that truncates in much more rapidly. Or some of the work that Jennifer Carter is doing at the moment in the UK Biobank, when you're looking at the dietary data over time, you see a more rapid shrinkage. So this phenomenon underpinned then the basis of the Prospective Studies collaboration that Sarah Lewington led, and how we analysed the data that took account of that. And in the 1 million people in this survey, about 1/3 of them had resurvey data, and we saw the same phenomenon at the mean here of about 3 years later, of a difference in the range here of 100 versus 65, a ratio of the ranges of 0.65. And that shrinkage factor at 3 years, shown here in aggregate data, means that there will be a systematic underestimation of the associations if you just ignore that phenomenon. And as Sarah showed in the PSC, when you take account of that, the true strength of the association of systolic blood pressure with CHD mortality is double. So the Whitehall data subsequently led to this Framingham data, which led to this concept of looking at exposure periods and understanding what actually are you measuring, what is the risk period and what is the exposure period, and how to correct for that when doing age-specific analysis. And I think the rest of that is history. You're familiar with those plots. While individual risk factors then in prolonged follow-up lose some of their predictive value, when you aggregate these into total risk, here's the shown crudely, is if you dichotomize the risk factors into none, 1, 2, 3 risk factors, and then look at those 3 risk factors. So despite this variability, you see this 8-fold difference in your 10-year risk of CVD death, or a difference in your lifetime risk of 38% versus 55%, or a 10-year difference in your life expectancy. So despite how crude the measures are, dichotomized in this way, 3 versus 1, you see that translates into that 10-year difference in life expectancy. Rather than taking these aggregates of dichotomously classified risk factors, if you put them together in a score, a total cardiovascular risk score, and look at the extremes of the distribution to try and estimate what would be ideal cardiovascular health, what would be the magnitude you might get. Say the lowest 5th percentile compared with the upper 5th percentile. Here you can see almost a 20-fold difference in your 10-year risk, the risk of dying of cardiovascular disease in the next 10 years, or a doubling in your lifetime risk, 33% versus 61%, and here about a 13-year difference in your life expectancy. So however crude these measures, measured on a single occasion, they can still translate into very meaningful changes. So these were the lessons we learned from the Whitehall study, and then try to apply these in the PSC and now in Kadoorie. So here's just taking one of those plots to say, here's the impact of that, and you can reflect on this plot when in the light of what you saw for the UK mortality rates. So here you can see that 88% survival at age 70. So what's that? 12% versus halving. So you can see the impact of death in middle age for those in the lowest fifth compared with the upper 5th percentile, and see the magnitude of the effect, or a difference in the median survival of about 14 years in life expectancy. So these risk factors, which we said we had this halving, that only half of cardiovascular disease was explained by the 3 risk factors. We haven't done any corrections for regression dilution here, but yet they could translate into this magnitude of differences in cardiovascular disease. So that's the lessons from Whitehall for China Kadoorie Biobank. 500,000 people, 10 regions. We said 25,000 were resurveyed in 2011, and then I joined this when we were planning for the second resurvey then for 2013. I talked about the deaths already, but the main benefit of Kadoorie is these 1.5 million hospitalizations. So these are coded hospital events, of whom 25,000 have died, but 43,000 are strokes, 31,000 are CHD events, and 32,000 other vascular disease events. So when you see this side by side with Whitehall, you appreciate the magnitude of these biobank studies in terms of the scale, that 30-fold difference in the numbers. But actually, then you look at the impact of those numbers of strokes, and then the kind of results that you'll get out of those. So this is the promise. This is the promise of what we hope to reap in that. We talked about limitations in observational epidemiology. Well, Mendelian randomization has been a great strength to us to help address many of those limitations in observational studies. And we had a lovely lecture on this earlier last week at a whole workshop on genetics. So I know many of you were here and heard that. So in China Kadoorie Biobank, we've had 3 tranches of genotyping. In 2014, we had 384 candidate genes. So basically, all the GWASs that we could get our hands on, coronary disease, stroke, blood pressure, lipids, diabetes, COPD, BMI, we took all the lead SNPs from these meta-analyses and put them on a panel, 384, and Iona and Robin are leading this work, and included then some interesting ones, the gene that encodes the LPPLA2, and our MTHFR, the gene that encodes the homocysteine differences. And these have been immensely informative. We got funding from the MRC now to do nested case control study on stroke, 5,000 ischemic stroke, 5,000 hemorrhagic stroke, and 1,000 MI cases, compared with 10,000 controls. And we can then supplement the incident cases that we get in these 384 with this nested case control. So these analyses will show you some of these. These ones are still in the pipeline, and the bigger and even more interesting ones are the new panel then of the GWAS panel, 800,000 SNPs in the whole 100,000 overlapping with the 25,000 that are in the second resurvey. So this is to show you some of the promise that hopefully that will come out of China Kadoorie Biobank study. We talked about blood pressure earlier, and this slide, which work we've done led by Sarah Lewington, and shows that if you dichotomize the population into hypertension, so defining the, we know that the association is log linear, but if you dichotomize them into hypertensives with a blood pressure greater than 140/90, about 1/3 of the population have hypertension in this population. So in China, so over the last 2 decades, the prevalence of hypertension has increased substantially in China. We're now at levels comparable with those what we see in North America or Britain. But the major change is that most of this, more than half of it, to almost 2/3 of it, is undiagnosed and untreated. Here, the solid blue bars, here's males, here's females, is the undiagnosed, untreated, and this one uncontrolled, and the white tips at the top are the controlled. So you see the magnitude of the problem in China. It's huge. It's absolutely huge. That rising prevalence with increasing age from 1/6 up to about a half. So looking back to those old blood pressures and the similar mean values that we saw in Whitehall to what we see here, and the fact that none of this is treated, none of this is recognized, and of those that are recognized are not treated. So how can we use our epidemiology then to get population change, to look at that impact of those on the stroke? We can only do this by publications and then trying to use those publications to influence change. Sarah did these analyses then relating the hypertension, uncontrolled hypertensives versus not for deaths. So we said we had about 8,700 CVD deaths. You see this almost 4-fold higher risk, under 60, 3-fold 60 to 69, 2-fold 70 to 79. And then you can look at the impact of these. If you take that and look at the impact of, what's the impact in China of uncontrolled hypertension in the year 2000? We've got these population attributable fractions of about half, overall of about 1/3. And you can see that almost 750,000, if you add these up, of the deaths per year are due to uncontrolled hypertension. So if you could get a policy that would shift the mean levels of blood pressure, you'd have a huge impact on the numbers of deaths from vascular disease. When you correct for regression dilution, as shown here, you can then get inferences about differences more reliably about hemorrhagic versus ischemic stroke. And we have a 3-to-1 ratio of these within our population. Blood pressure, for unit difference in blood pressure, so you have a 3-fold difference in hemorrhagic stroke and a 2-fold difference in ischemic stroke. Blood pressure has been linked to diabetes, to chronic renal disease, to many other conditions. So come back to that first slide. How do we interpret those data? Well, the genetics can help us elucidate to the extent to which some of these associations are causal, and can elucidate whether the reality of those differences between ischemic and hemorrhagic stroke. These are important questions. So using the genetics, we posed 3 questions. In the preliminary analysis of the 384 SNPs, we had 22 SNPs that were GWAS hits for systolic blood pressure, and we use these to construct genetic risk scores, and then look at the impact of a genetic risk score versus the usual blood pressure after correction for regression dilution, or the baseline levels of blood pressure, and then look at the effect of these genetic risk scores on both vascular and non-vascular mortality. This doesn't project very well, but it's just the individual SNPs had a difference of about 1 to 2 or half a millimeter difference in systolic blood pressure. If you aggregated them all together, we got a 5 millimeter difference in systolic blood pressure by combining these 22 SNPs in a score, and then you could relate that score to vascular and non-vascular mortality in different ages or in different components of blood pressure, of vascular disease. So taking that genetic risk score, you could divide it into thirds. So the difference between the top and bottom third is about 5 millimeters of systolic blood pressure. And you see these strong associations with ischemic and hemorrhagic stroke and major coronary events. And we take the slope of these lines, which I'll show you in the next slide, then to give you those estimates of the hazard ratio for a unit change in systolic blood pressure. So take the bottom line here. It's a busy slide, so I apologize for this. Major vascular events. So we're comparing here, so any vascular event, 29,000 cases. What's the difference for a unit change in baseline blood pressure corrected for regression dilution bias, usual blood pressure, and the genetic risk score. So the same unit difference. You see this increment here of this is double this one, and this is almost threefold greater. Those blood pressure, the associations we know attenuate with age. So the strength of the association with major vascular events occurring under 60, 60 to 69, 70 plus, 20%, 15%, 9% excess risk. If you look at the impact on the genetic risk score, you get a constant effect of about 25% or so. And you then can compare the impact of the differences between hemorrhagic versus ischemic stroke, or look at then the impact of vascular disease on top, and then some of the non-vascular associations on the bottom. So I'm sorry this doesn't project that well, but you can see roughly of the vascular ones here. Here's major vascular events at the bottom, what we showed you the last time, 1.27, and these pretty much stack up. There's 1.35 here for hemorrhagic stroke, 1.26 for ischemic stroke. But chronic kidney disease, or diabetes, the hazard ratio is 1.00 for diabetes. So the associations that are reported that hypertension might be linked to some of these other diseases, when you look at the genetic data, there's no support for these at all. So the genetic data is immensely valuable. Not only has it shown that the strength of the associations were threefold greater than the baseline systolic blood pressure, or twice those for the usual systolic blood pressure. But what it means really is that blood pressure over the life course is much more important than what we believed. That it really highlights the real need to implement effective strategies to try and lower systolic blood pressure. And genetic data then can help demonstrate some of the associations between blood pressure and these non-vascular outcomes were non-causal. One of the other areas that we've worked on has been the discrepancy between observational studies and randomized trials. And we've in CTSU studied the antioxidant vitamins and looked at these in the heart protection study, and then done meta-analysis of those trials, including the HPS and all the other trials for beta-carotene, vitamin C or vitamin E. And there's a pattern emerging, likewise with homocysteine, the prospective data or observational studies showing positive associations of elevated homocysteine with cardiovascular disease. And then you come to the trials showing no effect of the vitamins on vascular disease. We've working with Joseph Thompson and John Anderson, and Whitehall data showed nice strong associations of vitamin D levels in plasma with mortality rates from vascular and non-vascular causes. Other people have looked at the associations with fracture. We'd very much like to do randomized trials looking at the effect of vitamin D on risk of fracture, and indeed include other vascular outcomes. But there's a pattern emerging here where we repeatedly get this. We find associations in observational studies, and yet we fail to confirm those in randomized trials. And what I wanted to drill into a bit more detail is the homocysteine story. And really, when I did my doctorate on this, we had 120 cases, and it was published in the New England Journal. I came 3 months later to Richard and Rory, and I was clutching this report, which I was very proud of, because it was so hard fought to do this kind of work in Dublin, to recruit cases under 55, do methionine loading tests, do skin biopsies. We did a 2 type of case control studies. We compared cases with hemorrhagic, with stroke, heart disease, peripheral vascular disease versus controls, and then looked in parents of affected children who had homocystinuria, and then looked for carotid artery disease in their and other metrics of surrogate measures of vascular disease compared with controls. And that report, which reported a 2-fold increased risk of CHD, stroke, and peripheral artery disease. As I said, I was very proud of this, and Richard looked at this and took the paper and said, well, it's 120 cases, that's not serious evidence. Well, so to perhaps chastened by that comment, then we kept on for 2 decades trying to get an answer. But within the mid-1990s, there was a euphoria about this, and the meetings that I attended, that small study was rapidly replicated in 17 other studies that suggested that a 5 millimole lower homocysteine, micromolar lower homocysteine might be associated with a halving in CHD risk. Working with Sarah Lewington, and then when we looked at the prospective data, that was less extreme than the retrospective studies. When we got the individual patient data of the prospective studies, we still saw an association of about a 10% difference in CHD, 20% difference in stroke, and then we set up our own trial, the search trial, which Jane led, which took 12 years from start to finish. The mean duration of treatment was 7 years. So it took a long time to try and have sufficient power to be able to confirm or refute the association that the observational data suggested. And alas, as you know, the meta-analysis of those trials showed no effect on lowering homocysteine. So we thought this was the pitfall that we had. I remember the eureka moment of hearing these results, and something you're interested in this hypothesis, you'd like to do this. This had more than a passing interest. There was folic acid, of course, is very beneficial for reduction in neural tube defects. It reduces these by about 75%, so it's a very effective intervention, and worldwide almost all countries have fortification. So the impact of these findings, whether we not only had a benefit for neonates or children, but also had some benefit in adult life for these fortification strategies that were planned. So there was real scientific interest in these questions. Now, just when we thought the question was all sorted out, then we had this surprising result from the Chinese trial, the Chinese primary prevention trial, that reported in March this year. It doesn't read very well here, but you can see enalapril compared with enalapril plus folic acid, and it gave a hazard ratio here of 0.79. A surprising result. So 20,000 people randomized to folic acid 0.8 milligrams versus placebo for a 4-year period in China, and 20,000 people was associated with this difference in stroke rates of 292 versus 355, but 21% reduction in stroke, and then that stroke largely contributed to these 324 versus 405, and a similar magnitude of effect on major vascular events. So if you contrast that with our meta-analysis, these are nice plots that Jim Halsey has put together. There's 48,000 in all the remaining trials, and you can see here these hazard ratios: 1.03 for coronaries, 0.94 for stroke, and major vascular events 1.01. So if we were to merge these together, it would shift the conclusions of that study. So maybe we got it wrong, that in fact homocysteine lowering is beneficial for stroke, but not for coronary disease. And that this study, which was a primary prevention trial, these were hypertensives at high risk of vascular disease, were randomized to folic acid. These were, in the main, secondary prevention studies, people who had prevalent disease and were preventing recurrent disease. Was that the conclusion? These were the issues that were And the accompanying editorial that went with this talks about one well-designed trial trumps the rest, which was a by our Harvard trials, grating editorial to read it. So is it true? Well, there's some very odd things about this trial, not least when you look at this meta-regression here, at the proportion of vascular events, the proportion of deaths due to vascular disease. You can see here about 13% in a primary prevention trial in China. So it's something really odd. I showed you the prevalences in China Kadoorie Biobank, but in a hypertensive enriched population, so selected on the basis of hypertension, we would have expected these as way over here. I saw this report on several stages, and there were other quirky things about the trial that we haven't really got to the bottom of. Was this real, or was there a bias in the ascertainment of the outcome that could have distorted the results, that could explain that discrepancy between the fatal and non-fatal events? We will perhaps never get to the bottom. We've had multiple correspondents trying to get to the bottom to see, was this real, or indeed should we believe it? Well, one way to address this then is through Mendelian randomization, and promises and pitfalls. So coming back to many of you in this audience have heard us talk about this before, so we can gloss over it. So this gene that encodes the enzyme in the remethylation of homocysteine to methionine, and typically 10% of the Caucasian populations have, if they have the TT variant, they've got a 20 to 25% homocysteine excess, or about 3 micromolar. And that's the difference you typically get with folic acid. So you can use the Mendelian randomization studies of this variant to assess the effect on CHD or stroke of the lifelong differences in homocysteine. So here's you're allocated at birth, as Gemma showed you in the workshop in Mendelian randomization that most of you attended last week. You're comparing event rates in those with TT compared with CC. They have got a 3 micromolar difference in homocysteine, and that's exactly analogous to what you get for 5 years of treatment on average in the randomized trials. These are for life, and these are just for the 5-year duration of treatment, and you're looking at the event rates in either of them and then comparing them. Now, for coronary disease, there was a conundrum, which the trials, many people didn't accept the trials because in the published data meta-analysis, there was a suggestion for coronary disease that there was an excess risk in Asian populations, but there was no excess in all the remaining populations. And eminent people like Nick Wald felt, on the basis of that, everybody should have a polypill. The polypill should contain folic acid, as well as blood pressure lowering and statins and antiplatelet therapy, largely based on these sort of data. And in work then that we did with Derek Bennis and Sarah Parrish, when we got the GWAS data from the Cardiogram plus C4D consortium, here we'd almost, 48,000 CHD cases. In the unpublished data, there was no association at all, and we could completely refute that. And we could then confirm that this aberrant finding that we saw here was due to publication bias. And exploring those Asian studies, it was mismatches between cases and controls, or being out of Hardy-Weinberg equilibrium, or in the genotype, or the frequency in the Japanese population completely at variant with all the others that explained the reasons. So we were confident then that we had refuted it for coronary disease. So the question then remains for stroke. So the Chinese primary prevention data showed this data for stroke. And in China, there's an overall prevalence of the TT variant of about 16%, but it varies from 42% up here in Hunan and 34% in Harbin, down to 4%. So it's a tenfold difference in the prevalence of the variant. So you heard last week about the importance of population stratification. So failure to take account of this widespread variation can give you spurious results. And here, when you look at the findings here, based on our preliminary data of 7,000 strokes, 1,000 CHD events in the panel of unrelated individuals with the 384 SNPs, if you take the base model, you see 1.38 for TT versus CC, risk for stroke, 38% excess, and that's attenuated down to 1.10 after adjusting for region. So the chi-squared has dropped here from almost 80 down to 5. So there's a huge shrinkage in the chi-squared, in that strength of the association with just crudely adjusting for region. For coronary disease, the effect goes away completely. So if we could then, we're now awaiting the results of the GWAS, where we will double our number of cases. As I told you, of stroke, we'll have 10,000 additional strokes compared with 10,000 controls, and we'll have principal components in addition to those regions. So rather than having just a crude measure of region, you'll be able to drill down to between the regions and see, in fact, is this attenuated away more completely? It's a complex story, and at the moment we can't completely exclude the possibility that in fact it might be real and that we can't reliably exclude it, or indeed it's residual confounding due to some imprecise correction for population stratification. So it shows the sort of challenge. So genetic data is indeed helpful, but in fact sometimes it doesn't quite solve the problem. Where are we now? Well, we've shown, the trials have been very clear in Western populations, shown no benefit for reduction of cardiovascular disease. The trials, when our colleagues have come back from China, or we had visitors here from China, neurologists, 14 neurologists here for the FORC meeting at the end of June, they were completely convinced about this. This is a landmark Chinese trial. It's 20,000 people, it's published in JAMA, it's properly designed according to them, and they're all recommending folic acid for prevention of neural tube defects, for prevention of stroke. What we've shown is residual confounding, but we can't exclude a causal relationship. And really the only way we can resolve this is to try and do another trial. And this is what we want to do, and try and bring together the work we're doing on blood pressure and homocysteine, and do a factorial design trial of 2 by 2 by 2 factorial design trial. Say, what have we learned from Whitehall, Kadoorie, about the importance of blood pressure, of mildly elevated systolic hypertension, and do a primary prevention trial in high-risk individuals selected on the basis of their total coronary vascular risk score. And working with Li Xinjiang, she's got a unique cohort where she's screened almost 2 million people and got the blood pressure, cholesterol, smoking, estimated these risk scores. And it's relatively easy to do a low-cost trial, a very simple trial, then replicating that folic acid versus placebo, LDL lowering versus placebo, and more sustained blood pressure or intensive blood pressure reduction versus usual care, using some sort of a low-cost strategy. So Jane and I want to go to China in November and spend a week with Li Xin, trying to help and then continue on this dialogue that we've had, trying to get the protocol for this trial right and try and resolve this question, and maybe with the blood pressure lowering arm, get an intervention that on a frugal basis, a low-cost intervention that could then change the way blood pressure is managed. And equally, our emerging data for LDL and the importance of LDL for ischemic stroke in China Kadoorie Biobank, which you'll hear about on another occasion, look at the importance of LDL cholesterol lowering for prevention of stroke and indeed these other vascular events. I'm conscious of time. I've gone. One of the key things we learned in the study is the second resurvey. We looked at other surrogate measures and a range of surrogate measures, and the carotid ultrasound had been immensely informative. Here we can measure plaques and we can measure thickness of the intima and media, this wall. These two parameters are only loosely correlated with each other, about 0.43. So now we have a new paradigm for biomarkers. So we have the risk factors influencing these surrogate measures, which in turn are biomarkers for stroke. And we see differential effects of these on these outcomes, and you'll hear about this on another day. Sarah is going to present this on another day. But we looked at a range of intermediate factors, and these carotid plaques are immensely informative. Just 2 slides to show these, that they increase linearly with age, you can see one third of the population had these plaques that ranged from 70% to 61% here between age 45 and age 75. And these plaques varied threefold by region within China. So there are factors there that must explain that variability in the plaques that we haven't discovered. They also vary threefold by categories of blood pressure. Here's the categories that we looked at here, this sort of step 1 category. So this secondary survey is a unique resource then to study these biomarkers. Procardis was a long time. It was a study where we had to screen a lot of individuals to get blood, to get our base collection of cases, 4,500 genetically enriched cases compared with the controls. And 10 years later, then we got this nice circus plot summarizing the major gene hits. So we aggregated our 4,500 cases with another 42 studies to generate this collection in total of 61,000 CHD cases and clarify the genetic architecture of CHD. Lp(a) was this one here. It was the single variant that had the strongest association with coronary disease. And we were fascinated by this Lp(a). It was an elusive protein that's around for half a century. And this kringle structure here, out to the side range, varies tremendously within individuals and varies between populations. And this is largely genetically determined. This is the LDL. So its function is not known. We don't know what it does. Very different sort of mean levels in different populations. But in Procardis, if you had one variant or two variants, that was associated with a doubling and fivefold increased risk of coronary disease. So we had no genetic factor that was as strong as that. So now there the advent of new agents that specifically lower Lp(a), and these are agents that we're interested in pursuing. Now we're interested in to see what was this association in the China Kadoorie Biobank. Well, we see patterns here of a 1.32 per 100 nanomole difference in Lp(a). So Lp(a) only affects about 1/5 of the population at the extreme level. So they have the excess risk, and the others are all bunched down here. These ones are compatible, those estimates, exactly as what we see in Western populations. And then for ischemic stroke, it's about half that, but again, statistically significant, showing Lp(a) predicts both ischemic stroke and a risk of MI. So this data has prompted a sort of a program to try and understand look at the transethnic comparisons of the proteins that ApoA isoforms. We're doing a series of isoforms in our China Kadoorie Biobank and then relate these to the levels of Lp(a) and then relate them to the genes. And then by that basis, try and understand what is it about Lp(a), how does it cause stroke, how does it cause ischemic stroke or MI, and what's its function in normal people. One of the other lessons we learned from Procardis study was, I'm coming to the end now, was the importance of IL-6 and these proximal cytokines that influence the levels of CRP. So CRP is widely used biomarker, but the more proximal cytokines that influence the levels of CRP there's causal support for those. So we planned a series of proteomic studies then to try and study some of these inflammatory proteins. We put in a grant to look at these for ischemic stroke at the moment, where these new panels now. So the repertoire of biomarkers has increased substantially. So instead of focusing on single ones or a handful in Procardis, largely with the genes, we need to catch up with that genetic data and then find the proteins that underpin those genetic associations that we've reported that are still anonymous. And there are opportunities here with 270 biomarkers in one panel or 4,000 anonymous proteins in another panel. So we can plan these nested case control studies, select out groups of cases, ischemic stroke compared to controls, coronary disease compared with controls, compare differences in these proteomic inflammatory markers, or indeed likewise for other factors. And now we can look at our exposures as we've done with Mendelian randomization and see the new era we're in now of characterizing exposures, of relating DNA to proteins, to metabolites, to disease. Our long-term aim is to try and get genotyping on everybody in the cohort. It's a Ming's aim, and he'll succeed. He's very determined. And so these biobanks, what I'd like to end on is this note of promise. So for those younger students, or those of you who are here working on the biobank, you've got a much wider range of diseases you can study. You've got better power, you've got better disease classification, far better patient stratification. So epidemiology has improved greatly in my time in CTSU. We've got a much better understanding of the exposures from integrating the genetic with the plasma to understanding the pathways, understanding the mechanisms, and that is helped them design the trials to test some of those questions. We hope we can identify novel biomarkers as therapeutic agents. We can look at predictors of drug response, differences in haemorrhagic versus ischemic stroke. When you give aspirin, whether there's a test that could predict whether you might be at risk of having a bleed or not. Those are realistic options. But we need bioinformaticians, we need bright and capable people to help those of us, and all of us, were struggling with the data handling, the analysis, the interpretation. This is a moving area. It's a challenging area of systems biology, and we're working with the Clifton, the people in the Green Building, in medical engineering, to try and look at new ways to add to our multivariate analysis. So I'll stop now and say these classical risk factors are probably much more important than we widely believed. I focused here on blood pressure. Richard and others have demonstrated the importance of smoking. I haven't talked about lipids here, but other people will talk about that in future fora here. Genetic studies have reinforced the importance of long-term differences in these systolic blood pressure. I think the combined analysis of the genetic and biomarkers have helped clarify the relevance of some of these elusive biomarkers. And these new cohorts, CKB, likewise UKB, are really unique resources to get new information about old risk factors as well as new risk factors. And my chief thanks then is to all of you who have made this journey possible. It's not possible for any one individual to do this. I've benefited tremendously from the team, and many of you are here in the audience who've contributed to this, and thank you so much.